The W boson is one of the particles responsible for transmitting the weak interaction. It was discovered in 1983 at CERN by the UA1 and UA2 experiments on the SPS proton-antiproton collider, leading to a Nobel Prize for CERN's Carlo Rubbia and Simon van der Meer. So why are we still measuring the mass of the W boson after 40 years? Well, for two reasons. We want to know the mass very precisely, and measuring it precisely is actually very, very difficult. Our best description of particles and their interactions, the standard model of particle physics, is overconstrained. Now, what do I mean by that? Well, if I take a wheel and I measure its diameter and I measure its circumference, well then of course the circumference has to be equal to the diameter multiplied by pi. If it's not, then either I'm measuring wrong or this is not a wheel. And that's what we call an overconstrained system. The measurements cannot be just any two numbers. So you can imagine the standard model like a cube. We have all these parallel sides and we're trying to measure their lengths as precisely as possible by measuring masses of different particles, interaction strengths. And then at the end we're trying to see if it's still a cube. Because what if the ends don't meet? How could that be possible? Well, that's possible if there's a new theory, new particles, new interactions that we haven't taken into account. So this way it's possible to see a new theory without discovering any new particles, but just by checking that things in their current theory don't agree. But for that we need all the measurements to be very precise. Trying to measure the mass of the W boson is like trying to measure the length of a stick blindfolded and holding it with only one hand. As opposed to trying to measure the mass of the Z boson, the other particle that transmits the weak interaction, which is like trying to measure the length of a stick by holding it at both ends with both hands. Now, what do I mean by that? The Z boson decays into two muons. And these muons can be measured very precisely in a particle detector, and from this measurement we can establish the mass of the Z. Now the W boson decays into one muon and one neutrino. And the muon can be measured precisely, but the neutrino cannot. And so we currently know the mass of the Z boson with a precision about 7 times better than the mass of the W. So how do we measure the mass of the W then? Well, let me take as an example the method used by the CMS collaboration in the recent W measurements. Let's first look at the Z boson again. So for the Z, the measurement is quite simple. We take the momenta of the two muons from the decay of the Z, and from these two momenta we can calculate what's called the invariant mass of the two muon system. You can plot this invariant mass for many, many pairs of muons, and you'll get a peak at the mass of the Z boson. There's some subtleties here, but basically if you measure the momenta of the muons correctly, then the position of the peak is the mass of the Z boson, and that's it. Now for the W, we only have one muon. So you cannot make an invariant mass plot from just this one muon. So what if we just try to simply plot the momentum of this muon? So you're also going to see some peak-like structure, but interpreting that in terms of mass is much more complex. The position of this structure will change with mass, but you cannot simply read the mass of the plot. So what you have to do is simulate this momentum distribution for different values of the W mass, and then once you have the observed data, you can check which of these simulated plots matches your observation the closest, and that gives you the mass of the W. Now the complication of this measurement is that it strongly depends on theory and on simulations. So we have to have very, very precise modeling of the physics processes happening in the proton-proton collisions in the Large Hadron Collider, and we have to have very precise modeling of the response of the particle detector. So state-of-the-art theoretical calculations and state-of-the-art simulation of the detector are critical for getting this measurement right. This really is one of the hardest precision measurements done in the Large Hadron Collider.